Hello, in this video we would cover an end-to-end ML project. Okay, so what this video assumes, this video won't be teaching code like Python or a specific framework. It won't also be teaching machine learning. So I assume that you're familiar with Python and machine learning terminology. So what I will explain here is the logic and engineering decision I took throughout this project, how I went from a given idea or problem and cracked it down and went step by step until I had a working product. Okay, uh, how I would like for this video to go. I don't like this video being like a one-sided discussion. So I'm talking and you're listening. No, I want viewers here to be active. So I want to benefit from you as well. So if you see anything that you don't understand or you think could be done better or that I did anything wrong, just approach me. I would leave all my contact information in the description or just like leave a comment on this video. Okay. So, uh, this project was inspired by a book called Building Machine Learning Powered Applications. And what the book explains, it just at its name, going from idea to product. So the book uh, basically does what we are doing here, but in a form of a book, and it also has code, and this is the repo for the code. I would leave all the links for everything I use here in the description, so you can find it there. The problem the author solved in the book is that how he created a machine learning model to give advice on writing better questions. So for example, when you are using any type of forum like Reddit or something, if you typed a formulated question, you are more likely to get better answers. So I was motivated by this and I created something a little bit different, which is a machine learning model that give you advice on how to write a better Python code in terms of like readability and styling. So let's take a look on how this actually works. There's a demo deployed on Hugging Face. So for example, let's go and just do a basic stuff, print hello world. Okay, as we see, the application gives you an estimated score about how uh, like good is your code, and it gives you then suggested improvements to make it better. So for example, the file appears very small. Consider the file appears very small. Consider adding meaningful structure. The code may be overly trivial. Ensure logic is meaningful. Introduce well-named intermediate variables. Okay, so let's say we applied some of these suggestions like that. We introduced a variable, we added some comments, we made the code like have more characters in general. So we made a longer file and we resubmit. And as we see, we actually improved the score here, and we get like different suggestions and so on. So the top score here is 10. So it's a scale from 0 to 10. Okay. So I then want to discuss about what will be the structure of this video. We will use the structure mentioned here in the repo. So we will begin with dataset exploration, then code, which is the Python code we are dealing with, exploration, feature engineering and initial model training, model iterations, recommendation generation, and monitoring and retraining. So it's not like a strict order. You can the video would be divided into these timestamps. You can jump into any one of them if you like, but I highly recommend you stick to this order because you know each section assumes you understand the decisions we made in previous sections. Okay. So how to go along with the video. Here you need to do the setup. You clone the repo and do the copy of the environment variables that will be used by the application, and you just skip this because this is for running the app. We won't run the app yet, and just run this pip install requirements to install the requirements required for the notebooks to work. So we'll start here. I will use VS Code as my editor. You can use whatever you like. So let's start with data exploration here. So first, when you have a problem, don't go ahead about like collecting your own data, because try to like use the work of others. So instead of going out and try to like scrap your own data and make unnecessary and do unnecessary effort, you can just use a dataset someone else previously collected. When I looked at Hugging Face, I found that there's actually a dataset called Python GitHub code. So we just load this dataset. Obviously, you can then collect data after you see initial success. So you may try the dataset you found, and you find out that your idea or your approach is actually fundamentally not working. So you didn't waste so much time. So what I'm trying to say here is try to minimize the time between idea and MVP, which is minimal viable product. So you are better off iterating than doing a one long trial. Okay, so this is the dataset, and the dataset was large, so we just got the test split, and we will further split it in the future. Okay, so this is the dataset. We look at its columns. We have text, which is the code, the repo name, the path, language, which is they are all Python, obviously, license, size, and score. Okay, we see that. So as we see, the dataset here has the following columns: text, repo name, path, language. They are all Python, license, size, and score. So the owner of this dataset didn't mention what does score actually mean, so we can't rely on it. So we remove unnecessary columns like language and score. Okay, and then here we look at the data. We see that all the columns exist, so all of them are non-null, so this is good. We start by looking at just a simple distribution for licenses. So this is like a compliance problem. So some licenses are safe to work with and train models on, and some are not. So to avoid this, we just select safe licenses here. So these licenses are the licenses you can easily use and manipulate in this project. So we pick them and remove other licenses here. We look at the distribution of the number of characters for each file. We see like this distribution with a skewed distribution with a long tail here is very popular with any type of text data. So if any of you have done NLP before, you will this shape would be very familiar to you. Okay, so we see here extreme files like 500,000 characters. So we just clip the dataset to 99% quantile, which is almost 75,000 characters, which is very good for us. And we see the new distribution. This is more manageable. We have like that, removed the outliers from the dataset. So now the next step is target generation. So for machine learning, you have like supervised and unsupervised. So this would be a supervised problem, but how you determine the quality of code in terms of readability and style. So it would be hard to, manually assess that, and it's even not 100%, objective. It's sometimes subjective. Someone may like the styling of some code and others may not. So for simplicity here, I decided to use a software called Pilot. So Pilot uses heuristics to give a score from 1 to 10 on the quality of the Python code. It examines like conventions, errors, warnings, and stuff like that. How would that be different from our model? First, Python, as I said, is a heuristic. Our model would be a machine learning model. And second, Python pinpoints the problems with your code. So it says at this line you did this wrong, fix it. But our model would give more like a general advice for the overall code quality. Okay. Here what we did is just loaded the dataset, and we have here Python editor module, as we see here. Basically, all functions we will use in processing or everything would be encapsulated here for using them more effectively in the future. So we can just import them whenever we like and use them. So let's take a look on data filtering. So this is just what we did when we were exploring the data. We have safe licenses here for my data frame, just gets rid of unnecessary columns, and filter data frame here picks the safe licenses only and clips the dataset at the 99% quantile. Okay. So we have two functions here, Python get Python text. So let's go and check it. So here get Python text. So let's give you an example for Python, how it works. So here Python data filtering, for example. As you see, Python here tells me this specific line is too long, make it shorter, and this line also. Final new line missing module docstring. So it gives a specific advice for line by line because it's a heuristic. And here you have a final score out of 10. So this is how Python works. Okay, now how we will use it. Here we will have we will run this command in the terminal. So we do this programmatically, and we just output in the JSON format so that we can use this output later, and we return it. So this is a get Python text. Okay. I then went and examined Python error messages, which we find here. Okay, but just click on this. As we see, there are different type of Python messages, like fatal, error, warning, convention. So for fatal and error, if the code contains these messages, it's not even gonna run. And giving a score for a code that is fundamentally flawed, it doesn't make much sense. And it wouldn't make even more sense to give you advice on how to improve it because it's not working in the first place. So we decide that if the code has like a fatal or error message, we'll just ignore it, except one error message, the error E0401, which is import error, because checking it would be very hard, because we then would need to install all the dependencies for each code block we examine, and dependencies may be large, maybe you would then have to deal with conflicts and versions and stuff like this. So we won't deal with any of this headache, so we just ignore this message. How to do this? You run this command, Python to generate RC file, and it generates this file, and we move it to the home directory to like propagate its effect to all subdirectories. If we take a look on this file here and we scroll down, you will find the disable here, the disable flag here, and you just add the error code so Pylon just ignores it. So when Pylon runs, it will ignore this code completely. Okay. So we get the Pylon text and we just examine an example from this. As we see here, we have like the error message and you have the statistics, and this statistics key here is very important because we get the types of messages we received from Pylon. So like that we can say, okay, if you have a fatal error, ignore the file. If you have an error, ignore the file, and so on. And you also have the score. So this statistics key is the most important for us. Okay, so then we created another function which is get Pylon score to then extract the score from the Pylon text. Let's take a look. Here we have get Pylon score. It returns -1, which represents null here if the code has fatal message or error message, and otherwise it returns the score. Okay, we apply this to our data frame. So now what we have is we have the text, which is the code. We like that we ignored all the files with -1, so we dropped them, and we have the Pylon text and we have the Pylon score here. So like that we successfully created a target for our problem. So we started with a problem, and now we can actually train some machine learning on it because we have a target. Okay, let's take a look on that's actually the number of characters, which is the only feature we currently have like have any relationship with the score. And we plot, you know, high score which has a score higher than the median and low score lower than the median. And as we see, as characters, you know, increase, we tend to have more of the high score. So it seems like there is a positive relationship here between number of characters and the score. So this is actually a good sign. We save our modified data set to exploration.csv here. Okay, you can find all the data in the data directory here, as you see. Okay, and like this we are done with target generation. So now we will go to split data. So we basically split data to train on the training set and test on the test set. You may be, you know, encouraged to do just a random split, but this is actually bad and may introduce data leakage. How is that? Here, when we do a simple train test split and we try to get the developers and the training set and developers and the test set, how can we do this? Remember that there was a column of repo name, so it's the developer name slash the repo name. So we split on this slash here to get just the developer's name, or just the, you know, the GitHub account name in this case. And when we see the intersection between the train developers and test developers, we see that they have 168 developers in common. Why is this bad? Basically, the model, when he sees let's say John, for example, John appears in both training and test set. So John is a very good and competent developer. He writes a very good Python code and consistently gets a high score from Pilot. So if John appears in both training and test sets, the model, when we try to test it on the test set after training, when he sees John's code, the model may realize, this is the code of John because this is his style, which I remember from the training. So let's just give him a high score. So the model actually didn't give him high score because he thinks this code is good, but it did so because he remembers that this style is from this developer, and this developer writes good code. That what the model learned from its training, it doesn't know otherwise. So we need to avoid this problem. So how we do this? We do a more sophisticated split here, a split by developer. We can find this function in the Python editor here. So as you can see, we use a group shuffle split, and we split on the developer. We add the developer column here by splitting at the slash of the repo name, as we said before, and we just return the training and test index. So like that, when we see the intersection between the two sets, we see that we have 0 developers in common. And like this, we avoided the data leakage, and we will use this split throughout the project with the test size of 0.3 and random state of 0 to have reproducibility in the code. Okay. Next, we start exploring the code itself. So we start by vectorizing the code. So as you know, machines only know numbers. So if we want them to process text, we need to convert text to numbers in some way. So the easiest way to do this is just to use a large language model and like input the text to it and extract the last hidden state, or the first output it produces as a vector. Okay, so if you don't understand how LLMs work, so basically we're just vectorizing the text. So we are transforming the text into a certain vector semantically. This is the most important thing to focus on here, semantically. So there's a bag of words model, but it just counts the words in a given text. So semantic meaning is better here because it understands what the code does, not just what words are there. Okay, so we just loaded the data, and here we have vectorized code. We can go and take a look. Here we have vectorized code. So I specifically put the imports of this function inside of it rather than outside the function like all other imports, because these packages are large in size. So you need PyTorch for this, and it's like more than 2 gigabytes or something. So I just kept them inside the function to and like during testing or during the application itself, we don't have to actually install these dependencies if we don't actually need to. So we will only install them if we call this function. Okay, so we use a tokenizer and the model, and we use like you know, a moving window to have different chunks if the code is more than the context window of the model, which is code BERT base in this case. This is the model we chose to vectorize our code. So again, I won't go into much detail about how LLMs work. So just understand that the embedding is a vector representation for the code, and it has dimensions of 768. Okay, so we generated the embeddings, and then we saved the embeddings because the generation you know, may take some time because you run a large language model, so it takes some time. So to avoid this bottleneck, we just save the embeddings here as well. You find it in the data directory, and then we split the data as we agreed. We will like have this split throughout the project. And then we use UMAP. What UMAP does, if you know what is PCA, which is Principal Component Analysis, you will easily understand UMAP. So it just does the same, but there are some differences. I will keep it out. Some techniques are, faster because it's not deterministic, so it can run faster with a little loss and accuracy for the separation. Some focuses more on the maximizing the variance and so on. So you can just UMAP is just, we have 768 dimensions from the embeddings. We can't plot this. The maximum thing we can plot is either 2D or 3D. So we collapse these dimensions into just 2 dimensions, and we make sure to we have a remaining variance as much as possible. Okay, and then we plot this plot here. We also function plot embeddings. You will find in data visualization in Python editor. You can find it. It's here. So here's the function. It just plots and makes a heat map or like a color for each data point according to its pilot score. So the more warm the data point, the higher the score. Okay, so as we see here, we have mainly, we can identify like this big cluster over here, which is mostly red, especially in this region, if you see. And you have also a big cluster over there, which is, have a lot of blues, so a lot of low score code. And you have like small islands over here and over there, which are also mostly blue. Okay, so these are interesting patterns to look into more thoroughly, and we can actually extract some information from. Okay, next we have cluster the data. So we already seen that there are actually some clusters. We need to do clustering more formally, in a sense. So we just load the data, we split the data, and we have here embeddings as a list. So we are just gonna examine the training data. So we here use k-means clustering to cluster the data. As we see, we tried like different ranges from 2 to 4 here. Okay, so what does the plot tell us? So when you're clustering, what are you measuring here? You are measuring the similarity in data points. So similar data points should cluster in one cluster, so they should resemble one entity. But when you specify the number of clusters here, so if you said I want 10 clusters, the algorithm would give you 10 clusters. So whatever you ask for, you get. But now you should determine, is the split or the clustering the algorithm did actually justified? So are these generated clusters actually clusters, or they are just like centroid driven? So they are splitted only because I said so. I said I want this number of clusters. This is why we examine multiple clusters to see like what is the range we get the most convenient or most reasonable structure clusters. Okay, so with 2 clusters here, we get this clustering. We have 2 clusters, so the big island we saw before and the smaller one. So this seems actually justified because we can, with our eyes, see that these 2 entities are different stuff. So what is this other plot here? It gives you the silhouette plot. What is this? It simply measures the cohesion and separation. You may like search for it online. So it just says for each point, how much is it close to the centroid of its cluster, and how far is the point from other points in other clusters. So ideally, you want each point to be as close as possible to its own cluster and as far as possible from other clusters. This is perfect clustering here. So the silhouette score reaches from -1 to the worst clustering possible and 1. So the larger the better here. So as we see, most of the points here are in the positive side. So we have 0 here, and most of the points are in the positive side. And we have the average score at about 0.6. So 2 clusters seems reasonable. Let's look at 3 clusters. We see here we got more negative. And also one more thing, the more proportional the clusters, the better. So we don't want to have a one huge cluster and a multiple of small ones. This may be justified from the plot. So this here is more subjective than objective. So you may actually see, as you see here, this actually a big cluster here. I can see it with my eye, and this is a smaller one. So this difference is actually justified. But if it's not justified, this is not a good thing. Okay. With 3 clusters here, we see we got more negatives, okay, here and also here. And we see the 3rd cluster was just by splitting the big island here. This doesn't seem actually that much justified because they seem to be one big entity, not 2. Okay, if we looked at 4 clusters, then we see this is completely wrong here because it again split it here, and with your eye there, doesn't seem to be any reason to justify this split. So it's mostly centroid driven. So it's a fake cluster here. So we will stick with 2. So we now conclude that we mostly have 2 main clusters to examine. Okay, this big one here and this smaller one here. Okay, let's go ahead and actually explore the embeddings. Okay, we have a file here called interactive plot. Okay, again, without going into detail, what it does, you see the plot we used before, which is the which plots red and blue dots depending on the pilot score. It's the same, but it's interactive this time. So if you click on a certain point, it opens a tab and shows you the code of this point and the pilot score of this point. So it's more interactive, so you can examine more easily. Okay, we have here this is the Java code which runs in the tab. Okay, so this part here, which is the Java, is mostly vibe coded. I'm not that good at Java, but yeah, you can read the file, it will make sense. Okay, let's go to see the interactive plot here. So we start by running the bouquet server. Okay, as we see here, this is the same plot we saw before, but this time when we hover over a certain point, we get the number of characters and the score of this point. Okay, so this helps us see what's going on. And if we click on a certain point like this, it opens a new tab. It tells us the index of this point and the pilot score and the code of this point. So let's start examining. So how we'll go about this? So okay, a good starting is to see 2 points that are very close together, which means they are very similar in code, but at the same time have different scores. So this would be the most interesting. So if we looked here, we see 2 points that actually very close, but one of them has a score of 9 and the other have a score of 0. Let's see. So we actually see copyright, OpenStack, migrate. So it seems like some database stuff. Okay. Let's examine the other point. Okay, also migration. So if we see here, we have migrate change set. So, and here we have migrations.create models. So it seems like they are the same author actually, but here as we see, um, at the first we had, which has the higher score, it has a lot of functions. So he divided the logic into functions. He is documenting, as you see here, a lot of documentation. uh, he separated the logic into functions. Okay, he still have like ugly chunks of code, but overall he has a lot of functions, comments, and stuff like this. And the file is long, as you see. The file is very, very long, and a lot of variables and stuff like that. The other one, we have a class, and I guess we have everything inside this single class. Yes. So we noticed that when you have, more um, when you have more uh, like, functions in the code, you tend to have higher score because this is more elegant and more readable. And when you have also comments, as we see here, this code is kind of documented. Here we have comments. This also is a good sign, but here you don't have any comments at all. Okay, this is a good um, starting point. Okay, we can continue here. Okay, so let's examine more points to see more trends. We go there. As we see, this point has a score of 10, so a maximum score here. This is suspicious. And we have a very close point to it, which has a score of 0. Okay, let's see. So the code in this area seems to be all related to this migration. And single class, no no comments, nothing, simply. And let's go to the point close to it with a score of 0, and we see something suspicious. It's the same migration. So how, this huge difference in score? We notice something here. So it basically has a line says pilot skip file, and when I did some research about this line, I found the following. This line makes pilot totally skip the file and give it a score of 10, so it doesn't even run the heuristics. It just gives it an immediate score of 10. So this is a big one, because if we didn't notice this here, we would have a huge you would have tricked our model. Now the model would be very, very confused, or the model would instead memorize this. So he would memorize the line pilot skip file, and when he finds any Python code with this line or something similar, it would immediately give him give it a high score. So like that, we kinda encoded the biases of Python into our model, which we don't want to do this at all. So here, what we'll do is, after loading the data, we see these points here. To just these are a couple of points I also found to have the same problem. As we see, this file has Python skip file and score of 10, and this is a very, very similar one, has a score of 0. So what I did is just I looked how many files actually contain the word pilot, which tells Python to treat this file differently, and I found they are only 127. So this is a small chunk. We can just ignore them. So I removed them. So remove skip files. Let's take a look. So remove skip files takes a list of the strings to skip, and just it drops files containing these strings. Okay, we did this and we saved a new dataset, which is embeddings version 2. and let's examine embeddings version 2 as well. So let's just interrupt the currently running bouquet server, and let's do this. Let's continue here. Let's zoom in a different. We see now that the data points are a little bit different because we removed some data points. Okay, let's take a look here. Okay, so this file contains just import. So now we have two options. We may include these. So if a file had just imports or comments or stuff like this, it would technically be a valid Python file, but it doesn't make sense because the purpose of the model is to give you advice on writing a better Python code. So if the file actually contains no logic, it does nothing, it wouldn't actually make much sense to score it as a Python file. So some files, configuration files or stuff like this, where you only like import something like this, or just a file with a lot of comments. So there is no logic, there are no assignments, functions, classes, anything that's going on. So just comments, imports, and none, executable. There's nothing executable here. So we also decide to exclude these. So we get this, and we look this are another data point we noticed, and as you see, it's all comments here, and the one we found here was all imports. But some files, as you see, has something called byte order mark. So basically, what is this? It's like the basic encoding most files use to identify how the computer or the machine reads the text file is UTF-8. This is the standard. So some files uses different encodings, and some of them include the type of encoding. The standard, if you are using UTF-8, is to include nothing because the machine already expects this. So at the end, this causes a problem with AST because it throws an error when it sees like this code which tells I am using this type of encoding. Okay, it can't process it properly. I will leave a video here from computer file explaining in more detail what is the encoding of text files and different types of them. Okay, so how we basically overcome this problem is in the has a executable code function. We just check for all different types of encodings. I found them with like a little searching online, something called Big Indian, Little Indian. We try to strip them, and if we failed and we face some error, we just return false. So this file we couldn't parse properly. Okay, so we apply the has executable code function to our code. So now the code that is running and has a valid logic, so identifying defining variables, creating functions, classes, so basically just doing something, not just comments or imports, would have true in this column, and otherwise it would have false, and we keep only the true files, and we save this new dataset for in the future we can easily load it. And we so you now just notice the cycle here. You start with some data set, you investigated some data points, you notice something, and you edit your data set and re-investigate it, and so on. So if we investigated the data set here, some more data points, I found out that files with more characters tend to get higher score. For example, files with docstring and comments tend to get higher score. Files structured as functions and the classes tend to get higher score. And if you actually go to pilot messages, you would see this is absolutely correct, because Pylint penalizes on having no comments or docstring, having um, um, no a weakly structured functions and classes. Okay, but it doesn't penalize for like characters. So what I think here, my assumption or my answer to this, why files with more characters tend to get higher score, because if you have a larger file, you spend a lot of time working on it, and when you spend more time working on something, you tend to give it more attention and write it in a more elegant way. Because if I'm writing like a small, really small Python file, like print hello world, for example, I don't need to give it much attention because I can quickly navigate the file. So I would just make something that as short and concise as possible. But when I start to get a larger file, I need to be more, you know, uh, uh, leave more spaces, write more comments and docstring, and split logic into functions, so that I don't like get a messy code that I can't read or understand later. So just this is my conclusion here. When you write a larger file, you tend to give it more attention and you tend to make it more elegant. Okay, so this is just my interpretation. You may have your own. This may be, far from truth, but it's a nice way. Okay, so like this, we have finished the code exploration part. Next, we have feature engineering and initial model training. Okay, see, so we loaded our the latest dataset we created. We dropped the columns that are no longer needed, like executable code, Pylint text, and number of characters. Okay, because we already extracted the Pylint score. Here we created a generate features functions. Let's go take a look. Okay, this is probably the largest file here. So we have features. We like thought they would be a good features from investigating the data points in the previous plot. So number of characters, code compactness, which how the ratio of lines to empty lines. So do you leave a lot of space between your code, or it's tight? Characters per line, comment ratio, has docstring, so the overall file docstring, not functions docstring. Variable ratio, average variable name. So do you have like long variable names that are ugly, or you have like very short variable names which don't actually tell what the variable does? Number of functions and classes, average function class name, average function and class number of characters, average function or class arguments, function class docstring ratio. Okay, so this class is relatively big. We would try to explain it basically. So code analyzer uses AST, and it visits each node of the code tree structure. So a node could be a function, a class, a variable. So any part of code could be represented as a node. Okay, we try to count the number of lines, number of empty lines, and we have as a list for function, one for classes, and one for variables. These are helper functions. So get text, it returns to us a specific text from a node. Okay, and number of characters, you give it a node and it gives you a number of characters in this node. And here count lines, the same idea, number of lines. Variables, we visit assign, so assignment for a variable of a certain node, and what we are trying to do is to add variables to the set variables. Okay, why variables is a set and functions and classes our lists here. So what is the difference? The set can't have two values equal to each other, so it has every value only once. So why is this? Now when dealing with variables, um, if I treat it as a list, each time you like encounter this variable, it would count it. I don't want this. So each time you would change this variable's value, this is a new assignment. So the variable would be count multiple times. So you may have only one variable in your code, but you changed its value multiple times, so it would be counted multiple times. So this is misleading. So using a set here overcomes this, but it introduces another problem. If you used now a variable, like for example in a certain function in your code, and you name it for example x, and in another function you use some other variable and you also name it x, this is completely fine in Python because these two variables exist in different scopes, but these two variables now would be counted as one variable. This is the downside of this approach, but I think this downside is has less harm overall than the first one, because most people don't do this, don't name the name two variables with the same name, because this is not wrong, but not something good either, I would say, because this may get people or even yourself reading the code confused. So I stick with this option to only count each variable name once. Okay. Visit function. So this is now function definition. We retrieve information about the function, like here the docstring, okay, if it has docstring or not, its name, lines, we use here the helper functions, characters, arguments, and the docstring, okay, and we append to the functions list. Same for class here, okay, we get the same information, and we get just the init arguments, and that's it. Okay, now we create another function here to deal with comments. This function returns the number of comments of the Python file, and then finally we use all this information to create the features. So analyze code here, we get comments, we get the analysis of the code using the class we created, and we just like stack everything nicely here in one dictionary and return it. Now let's go to generating the features. Here we have whole file features like characters. Okay, this is immediately we can find from the dictionary. Okay, we got from here. Code compactness, so we have the all lines minus empty lines, so this gives us the number of non-empty lines divided by the total number of lines, so it gives us the compactness of the code. So a compactness of 1 means you don't have any empty lines in your code. Characters per line, comment ratio, comment characters divided by overall characters, has docstring, just a binary variable here. And I don't want to go into much detail, you can read these, but I guess they are obvious. Okay, just skim through them, and we return our features. Great. Okay, so we apply now generate features on our data frame to get the features as we see here. Now we have our features like that. So now we can work with this. We have embeddings and we have features. We can input these into some machine learning model and get a prediction about the score. Great. Okay, so next we have training our model. Okay, what model would we pick? So you have here a regression problem. So it's either linear regression, random forests. You may use neural networks, but we want to keep it simple and always start simple. This was one of the most crucial ideas in the book I mentioned at the beginning, that you always do as little work as possible and then iterate and improve. Don't try to do everything at the beginning. So linear regression here won't be ideal because linear regression can't capture the nonlinearity in this problem. So we are dealing with text here, and this tends to have like nonlinear relationship with the score. So I want something to have more flexibility, but at the same time doesn't be very large and demanding in terms of, you know, compute, like neural networks. So the perfect here is a random forest. So we just use a simple random forest regressor here. Okay, we as usual load the data, split it. We now have a function called get vectorized features and label. Let's take a look. At just simply we have the pandas data frame, which has our features, and we transform it to array so we can feed it to the model. Here we have get vectorized features and label. Here if embedding is not in the columns, and we see why this now, because in the future we will decide to remove the embeddings at all, like completely. Okay, we vectorize them, and so if it's not embedding, if it's not in the columns, we just vectorize the features. Else we concatenate the embedding column alongside other features. Okay, and the label is just the values, so the array of the pilot score, and we return both features and label. So we do this for the training set and for the test set, and we train a simple random forest regressor. We won't bother with hyperparameter tuning right now because we first want to see the, you know, the baseline performance of our model, and then at the end we would do hyperparameter tuning for squeezing this extra performance. What does OOB score mean? It keeps part of the training data outside as a validation. So like that, when you get the error of the model you trained, it's more close to the testing error. Okay, so it just gives you a more accurate error or performance metric for your model, so it doesn't overestimate. Because if you trained your model on data and you tested it on the same data, you would get a high performance, not because your model is actually good, but because it's performing on data it already saw before. Okay, so this tries to minimize this effect. So when you get a performance on the training data, it's you know, it's not overestimation. Okay, we train the model, and then we here dummy is basically we are predicting the mean of pilot score. So this is the most stupid model you can get to predict some you know, continuous value, is to just get the data set you have and get the mean of the target value and predict this. This is you know, the basic this is not considered machine learning, it's just predicting the mean. Okay, so when we predicted the mean for training data, we got a mean absolute error of 2.5, root mean squared error of 3, and r square of 0. Okay, for the test set we got also a very high error and a very low r squared. Now for our model we actually get a lower error and a higher r squared, so our model is actually better than just predicting the mean, so it actually learned something. And for the test set we get even you know, a slightly worse results, but overall good. So we achieved something more than the predicting the mean. This get metrics here is very simple. We just get these metrics and return them as a dictionary. Let's take a look at it. So very basic, we just get the mean absolute error, root mean squared error, and r square from Scikit-learn here, and we just return them as a dictionary. Okay, we save our model to the models directory. You will find it here inside the notebooks. Okay, And then we now have a model, a working model, but it has different parts. So first we get the text, we get the embeddings, and then we get the features, and we vectorize the features alongside embeddings, and we input this to the model to get the answer. We want to encapsulate this whole process in only one function, so that we have a function that we give it some code and it spits out the score for this code. Okay, this is what get model prediction from text does. Okay, so we simply give it the row, which Pandas series for the code. Okay, and the feature generation function, we give it the model to use while predicting, and we tell it the embedding dimension we use, which in this case 768. Let's take a look. So here, model prediction. So first, we check if the code is executable, because, you know, as I said, we don't want to give someone advice for improving a code that is not actually working in the first place. So if it has executable code, we proceed, and if it does not, we return just an empty. These are the features, empty dictionaries, because there are no features, and a -1. So -1 means null here, the code's not working. Okay, if it's working, we generate features using the the generate features function we passed to the function. We vectorize the features. If there are embeddings, we just concatenate embeddings here after we vectorize code using code BERT base. If you remember, this is our embedding generation function, and we get the prediction using the model we passed also as an argument, and we return the features we created and the prediction. Okay. So if returned here, we see we just give it a simple piece of code, import pandas as pd, if true, pass, just to have, you know, some if statements, so means this is actually an executable code. And we see here it returned the features of the code, as you see, and the score. It gave it a score of 4 here. Nice, very nice. So we now have a working pipeline, if you would like to say. Okay, now after training, most people would jump, okay, now I have a working product, let's go and use it. No, you need to evaluate your model. Is it good? Is it bad? Where is it lacking? Where is it doing good? Etc. So we now jump to model evaluation. We load the features, we split the data, we get vectorized features and label for test here, because it's test, this is what we're gonna be testing on. We predict for the test set, okay, and we plot a residual analysis. So just we plot the residuals, which is the difference, the squared, the difference between our prediction and the actual value, and we now have we plot it against predicted values. Okay, so perfectly in a perfect scenario, you should have points scattered all over the place here without any trend, so they should be randomly scattered like that. Okay, but in this case, if you see like there's a downward slope, so the points are cut from here and cut from there like this, and this is actually makes sense. Why? Because here, as you know, the predicted value at 0, for example, the model would be predicting large values. So it would be predicting like 8 or 7, so you'd have a large gap in the negative side here. Okay, but as you progress here, okay, so we now plot the residual analysis, and it just plots the residuals, which is the predicted value minus the actual value. We plot this against predicted values. Okay, so a perfect residual analysis should look something like a random cloud around the like the x-axis here. So it would should be randomly spread. But as you see, the points are not randomly spread at all. they have something called hetero. Let me read it. I can pronounce it. Heterosidasticity. Okay. So what does this mean? It's the points start wide like this. You see that the scatter is wide from here, so points go from here to here, and it starts like funneling. So you notice like this. You see points are scattered here more than here. They are more compact here. Okay, this is bad because this means our assumption about the linearity of the model is actually not very correct. Okay, so this is the first thing we notice. Okay, the second problem here is we have asymmetry in residuals. What does this mean? As we see here, the negative residuals go down to -8, where the positive ones go up only to 6. So it means our model tends to overpredict than underpredict. So we said that error is actual value minus predicted value. So when the model overpredicts, the predicted value is large, so you get a negative error. So having more negative or more extreme negative errors than positive means our model tends to overpredict more extremely than underpredicting. Okay. So now we create a column called error, which is just the error, and add it to test for our next evaluation. So now we want to see what are the examples our model perform good at, what are the examples our model overestimates, so give them a higher score than they deserve, and what are the examples our model underestimate. This is the get top k function. Let's take a look at it. Okay, so we copy the data frame here, we create an absolute error column. First, the top performing would have the smallest absolute error. It doesn't matter if you are wrong in the negative or positive, as long as you have a small absolute error. This means you are performing good. The model is performing good in this example. Okay, so we first get the top performing, and then we get the most overestimated. So these would have the smallest in terms of negative, so smallest error, which would be negative error. Okay, and the most underestimated, which would be having the most positive error. We return the top k. So k here is an argument, the number of examples to extract for all of these. So we stick with 3 to just see the patterns. Okay, so now looking at the top performing examples. First thing to notice here, Python score for the top performing is almost around 5, so around the average score, and for the overestimated 0, and for the underestimated around 10. So this actually makes much sense. Why? If I predicted a score of 5, what is the worst error I can get? If the file turns out to be a score of 10, I get an error of 5, and if it turns out to be a score of 0, I again get an error of 5. So being close to the average minimizes minimizes your error at worst, so you get the lowest worst error. Okay, but when you start to being, you know, a low score, so for example 0 here, the model can predict 10, so it can be wrong by 10, and the same for high score. So if you have a score of 10, the model can predict 0, and now it's wrong by 10. Okay, so this is understandable here. So we notice that top performing files have average to low number of characters. So 3,300, this is low, almost 5,000. Okay, they all have comments. You can you know, notice more patterns here for sure, but these are just you know, some observations. Overestimated examples, average number of characters. What does this tell us? Having average number of characters tends to be a sign of a high score. So our model, when it sees average number of characters, it assigns this is a good code. Why? So very long code tend to have a low score, and very short tend to have also a low score. Why is this? So we discussed the short side before. When you write a small function or like a small file, you don't give it much attention, so you write something that works and just move on. And at the same time, if you write a really big file, you tend to make more mistakes. So the more code you write, the more mistakes you make. And because of this, the sweet spot is in the average. We will see what is actually precisely the sweet spot in the future. But for now, we understand this. The more you are have average number of characters in your code, this means you will give it attention, but at the same time you won't make as much mistakes. Okay, so overestimated examples also have comments. So comments are a good predictor for high score in our model perspective. Moderate average variable name. So here have like 11 characters, 9, so almost an average of 10 characters per variable name, which is good, enough to make the variable meaningful and not very long, that is, ugly and hard to remember or to write. Underestimated examples here have very low or very high number of characters, so this seems to agree with our thinking before, that our model thinks if you have very low, just to make something clear, if our model thinks that, this doesn't mean it's true. We are just trying to understand what our model thinks when it's making a prediction. Okay, so here 200, a low number of characters. We have here 26,000, very large. Here we have 1,000, so also a low. Okay, and very low or very high characters per line, as you see here, like 40 characters per line is considered a little bit long, and 15 characters is a little bit low. Okay, now let's take a look at feature importance. So what our model thinks the most important features for itself when it's making a prediction. Let's take a look at the function. So here we pass embedding dimensions as an argument. So to determine the feature name, we arranged the input features like this. We have the embedding, then we concatenate the features. So we would name the embedding vector, which is in this case resembles 768 inputs. You would name it by numbers, so like 0, 1, 2, 3, etc. Okay, and then we would have the features name. So we simply just do this here, and we extract the importances from the model, and then we create an importance data frame, and we sort by importance to get the most important at the top. Okay, we see here that some of embeddings are the most important for the model. So the embedding number 449 is the highest importance. We also see our variables are important. So variable ratio here, function class docstring ratio has docstring. These are among the high importance for the model. Okay, great. Now we have a model that takes code and outputs a prediction for the code's score. How we can transform this into a model that takes code and outputs recommendations to make the code better. Okay, to do this we need to use black box explainers. Black box explainers are basically like from their name, they treat a model as a black box. So we have here the input to the model and the output. They tweak the inputs to the model and see how the output changes. So for example, I have a certain code file which has, let's say, 2000 characters, okay? And I pass this code to the model. It gives me a score of 4. And then I try to tweak the number of characters and I make it instead of 2000, let's say 3000. And I take a look at the model's score and I see that it increased. Okay, so this feature helps increasing the model prediction. Okay, and I do the same for all the features. I start tweaking them randomly, increasing, decreasing, okay, keeping some of them fixed, and see how they affect the prediction. And the conclusion is that I tell you, like, for this exact example you passed, these features helped increase the score the most. How can I possibly know this? If I dropped the value of this feature down and the score were kept almost the same, I know this feature is not that important for the model. And if changing this feature radically changes the prediction, this feature is important. Okay, so black box explainer called black box because they don't care about what model you use. So you can use them with random forest, neural networks, linear regression, whatever. They don't care. They just tweak the inputs and watch for the output, how it changes. Okay, so one of the great black box explainers are Shapley. So Shapley values are related to game theory. I'm not gonna be explaining this here, so I left a video that explains it intuitively and a playlist that explains the math behind it. A great playlist, like watch the first half because he continues after Shapley values, so you can just watch from the beginning of the playlist until the Shapley values video. So they actually has a mathematical proof that this method work. Okay, this is the Shapley library package you can install. It's already in the requirements. Don't okay. Now we see we created a function called get shap data frame. Let's take a look. So basically we just pass the training dataset. So why does it need the training dataset? To extract. So we said that it tweaks the features. Okay, it changes them. So if it just did this randomly, it may tweak them into an unrealistic value. For example, characters in the file. I may have a file of a number of characters 20, and Shapley decides, okay, I will tweak this to have a negative number of characters. It doesn't know after all what is the normal range for this feature. Okay, another example, if I'm dealing with like a feature of age for a patient, for example, it's like 40, and Shapley thinks, okay, I will tweak it up to 200. Okay, no one lives to 200. Okay, so this is unrealistic. So I give it the training data to look at the distribution of each feature and just extract or tweak the values in the range of these distributions, so it doesn't actually introduce an unrealistic value. Okay, because this would destroy the model output, because it will see a value that it never seen before. Okay, so we get the explainer and we fit it to X test. So we just use the training here, as I said, to extract from, to know the distributions. Okay, but we actually process the test, because this is testing. We are evaluating the model. This check additivity is just to avoid some error that may arise when the sum of the Shapley values doesn't add up. Okay, so don't care about it. You can read about it in the documentation if you want, but it's not actually that important. Okay, and we just add feature names as we did with the feature importance. Okay, after this we get the Shapley values, and we can do a bee swarm plot. Okay, as we see, these are the most important features for Shapley values, and they don't necessarily align with the feature importance by the model. So if we see here, we have function class docstring ratio as the third most important feature, and here it's the eighth. Okay, so this actually is more accurate than this ranking here, because this what the model thinks is the most important, or the model this is what's the most important for the model's prediction, and this is the actual stuff. This is what Shapley found for this exact test set to be most important. Okay, now the next section is model iterations. Now after we got our working model, we now want to iterate to leverage the knowledge we know from the first model, where it lacks, where it struggles, and try to improve this in the second model. So now we generate more features. Okay, we load the embeddings, and let's take a look at the second feature generation here. So it's the same concept. Okay, let's take a look. So it's code analyzer, but we juiced it up a bit. So number of lines. Now we are tracking imports. We are tracking names, like total names and bad names. What are bad names? So names that are not following the conventions, like snake case for functions and variables, and Pascal case for classes. Functions, classes as well, too many arguments. So what we noticed is that actually the number of arguments is not actually a good sign. So averaging it, so you may have a function with like 2 to 3 arguments, okay, and another function with like 50 arguments. So maybe the average of the file is overall good, but the file itself from inside has bad styling. So you may have like very small lines and then very long lines. So the average is good, but the lines itself are not proportionate. Okay, so I figured counting the number of violations would be more effective than just averaging all the violations. So basically the same stuff: assignment, function definition, classes. Okay, imports. We this is the addition here. If you use the imports or not, so we count imports and used imports. Okay, the names, so function names, variable names, classes names. Okay, here extracting comments. Instead of comment characters, we decided to make it comment lines this time. Okay, analyze code, the same stuff. Arrange it in compact dictionary, and then we decided to add another functionality, which get line length standard deviation. So for styling perspective, when I'm looking at a code, at certain code, it would be more nice if the lines are all almost the same length. So you have like maybe a little bit longer, a little bit shorter, but if you have a large variation in the length of each line, so you have very short lines, very long lines, this is not very good. Okay, so this is an extra feature here. Cyclomatic complexity: how complex is your code? So the more if else statements and loops and branching of your code, this is higher complexity, and so you shouldn't have very basic code, and you shouldn't also have a very complicated code, so like 7 layers of nesting or something, because at some point this becomes unreadable. Okay, so this generate features, same function, but adding the new features we mentioned here. And okay, we will return to this in a moment. Okay, so now we generated the features, split the data set, and now we look at the continuous features, which are the numerical features here, and to see the skewness of features. So if the features are skewed towards one end, this is not a good sign. We need to do a transformation here. Okay, so we look at the distribution. For example, number of characters is skewed, as you see. So you have a long tail here, and the most of the distribution lies in this area. Code compactness, for example, is more normally distributed, but it still have, you know, some tail like this. Some other features, you know, like function, class, doctrine ratio, a lot of them have a value of 0. So they are mostly 0, function density mostly 0, long line ratio mostly 0, okay? And the target itself is skewed and has a lot of 0 values also. So what we decide to do here, features that in nature has you know, a continuous value, so they can have any value, not a specific range, we would do a log transformation on them. For example, characters, as we see here, line length, standard deviation, and cyclomatic complexity. But features which has a certain scale, so they range from 0 to 1, for example, or they has a certain value, so all the ratios, doing a log transformation on them would destroy the variance, because log on this small scale would decrease it, so it would squish all the values into a very narrow range. Okay, so what we'll do, we just treat them, transform them into binary variables. So for example, long line ratio, instead of counting the ratio between long lines and all lines, I would just have a binary variable which says there are long lines in this file or not. Okay, so they become a categorical variables. Now we take a look at the distribution after the transformations. Okay, now characters are you know, normally distributed. This is much better. And as you see, also line length, standard deviation, and as we see the new binary features here. Okay, this is good. Now we take a look at, are there any correlation between our features? Why this is bad? Because you are relying on two features to tell you the same information. So if you have two features that are highly correlated, they are redundant. Okay, they are mimicking each other, so you can you know, remove one of them and the other would do the same work essentially. So when we look at the Pearson correlation here, we see we don't have any strong correlations. So the most negative correlation is 0.35 and the most positive, if I can see, is, you know, 0.55. So there are some correlation, but not like huge correlation between any two variables that justifies removing one of them. Okay, so as we see here, for example, cyclomatic complexity have a, you know, moderate correlation with number of characters. You can reason about this. If I have a lot of characters, the other way, if I have a lot of nesting and a lot of complexity in my code, I should have a lot of characters, okay? Because I will need to write a lot of characters in order to have this complexity. We apply these changes. So if we take a look here, so generate transformed features. Basically, it just generates the normal features and then applies log transformation and binary transformation to the features we just mentioned, okay? And we keep them here at lists, so we can access the columns of features easily, the log transformed features, the binary features, and the list of transformed features. Okay, so this makes it easier in the future when we are dealing with our model. Okay, now let's go to train the second version of the model. So nothing to be done actually here. load the features, split the data, vectorize, train the regressor, and now we are comparing the performance. So did our modifications actually improve the model performance or not? So the training error version 1, the first version, is 1.9 here, 2.4, and r square of 0.33. For the second version, we actually decreased the mean absolute error here. Same for root here. It's a slight reduction, but you can count it. And we improved r square. For the test, here we have a test error of 2.5, almost 0.4. Here we decreased the test error here and also here, and we increased the r squared. So actually our new model has higher performance than the old model. This is a good sign. It's not a huge improvement, but it's an improvement. We save the new model. We tried in prediction here with the functions we explained before, and we see now it gives the features, and this is the score. Great. Now we go to the evaluation. Same stuff. Model evaluation. So residual analysis, as we see, we didn't improve the heterostaticity. I can't pronounce this word, okay, but we improved the extreme negatives. So the previous model had -8 to 6. Here we have -6 to 6. So the model is equally to overestimate as it to underestimate. Okay, so it's not leaning toward any way over the other. We look at the top performers again to look at patterns. Great feature importance. Now our new one of our new features has a high importance for the model. This is a good sign. The line length standard deviation here. Great. We look at Shapley. We see that a lot, that the last time we had like 3 or 4 of our features. Now we have 5. This is a good sign. The model is now relying on our manually generated features more than embeddings. This is a good sign. Okay, let's now try, the student versus teacher. So our model learned from Python. So how would it perform against Python? We try here on the test set with 50 examples. Okay, and this is a function of compare time. It just runs both Python and our model on the examples we provide and calculate the average prediction time, okay, to see the latency of our model. So for 50 predictions, the average prediction time for our model is 2.3 seconds, which is slow, okay, and Python is 1.1 seconds. So effectively Python is 2.5 times faster than our model. Okay, this is not necessarily a bad thing, but you would think that a model that gives you general information, not a specific detail about what is wrong, like Python, should be faster, right? Not slower. And this is like a valid argument here. Okay, so what is the bottleneck in our model? Basically, it's the generating the vector. So generating the embeddings using the large language model is the bottleneck in our pipeline, because it's the most compute intensive step. So in the third iteration, what we'll do is we will remove this bottleneck. Okay, so let's go here. We just drop embeddings and we save it as a new data file. Okay, the same stuff here. Now since this would be the model we start using in the remaining of the project, we would start using MLflow for experiment tracking. Again, I wouldn't be explaining MLflow here, but basically it helps you store everything about your machine learning process. So for example, you train the model, What are the parameters you used? When did you train the model? What are the performance metrics? What data set you use to train this model? So in the future, when you have iterations on your model and you get out multiple versions of this model, you can compare versions, push this model to production, make this model retrain, and do stuff like this, so you don't get lost in the machine learning realm. You just don't know this model trained on what, used what parameters, performed or produced what performance metrics, etc. Okay, so we create a simple SQLite database here for MLflow. It would be here in notebooks, models, MLflow. Okay, and we set the artifact. So artifact keeps the model itself and its metadata locally. Okay, and we create an experiment called random forest regressor. Now, as we said, after we seen success with our model, we now do hyper parameter tuning using Optuna. You can find so it just Optuna tries different parameters and do different trainings and tells you, okay, this is the best iteration I got simply. Okay, basic stuff here, cross validation. Okay, and here we start the run. What we log here for MLflow, the data set we used in training, the processing file, the feature generation file, the test size and the train test split, and the random state and the train test split. We start the hyperparameter tuning with the study. Okay, and after we get our best parameters, we train the best model and we use it to predict and get our metrics. Okay, and return them. And here we also log the performance of the model, so it's metrics here. Great, and we also log the best performing in the training with Optuna. This is the iterations, as you can see. You can also open MLflow UI in the web, but we won't do this right now. Okay, now to easily retrieve a certain model from MLflow, you can go to the experiment, look at the specific run ID and get the model. This is takes a lot of time, so what we do is that we register the model. Okay, and we can call it anything, and so we decide here to call the model name recommendation model, and we get the model the run ID like this, and we register the model and we give the model an alias. You can give it anything. We would call it production. Okay, because this is the model we will be using in production. Great, so it created a version 1 of the model named recommendation model. So we easily now can connect to the MLflow database and tell MLflow, give me the current recommendation model, and just give it to you. Okay, we now compare the third model with the second. We actually see a decline in performance. So we went from training error of this. Okay, so it's almost the same training error, but for the test we get a decline. So 1.9 to 2, 2.4 to 2.6, 0.43 to 0.36. So we actually has a reduction in our performance, but in the other hand we'll see that we improved the latency. So we save the third model, and now when we compare the third model with Pylint, what we get is okay, we save the model and we try predicting with it, and it works like this. Now we lost performance. This is bad, right? No. Why? Because as we'll see, we extremely improved the latency. So here in evaluation, we see again the residual analysis. We got this extreme negative back. Okay, so we see clearly we have a declined performance here, and the same stuff here again. Okay, feature importance. Now we removed embeddings, so we only have our generated features, our crafted features. This is for Shapley. So we see here the number of characters is the most important feature. Now, when we compare our model to Pylint, we see that our model on average takes 0.1 second and Pylint takes 1.2 seconds. So we went from Pylint being 2.5 times faster than our model to our model being 12 times faster than Pylint. This is huge. Okay, so we have a huge performance latency over Pylint. This is great. So the trade-off is not always performance metrics. No, there are other stuff you need to take into perspective. So I may have a very good model, but it's very slow. I can't use it in production. So I would accept an average performing model with acceptable latency. Okay. The next section is now taking the model we created and generating recommendations from it. Okay. So this is our last model and our last feature dataset. As always, we split, vectorize. Now we get Shapley data frame, okay, with both training data and training data. So we have training data as input and training data for reference of distribution, if you remember. Why this? Now we will try to investigate where for each feature, where does it have a positive impact on the score, and where does it have a negative impact. Why we would like to do this? Now, if we know, for example, number of characters has positive impact between 1,000 and 10,000, for example. So if the code gets a certain score from the model and we examine its Shapley values and we see that the characters affected this score negatively, and somehow we check is number of characters in the positive range, which is from 1,000 to 10,000. If it's larger than the range, so we advise the user to lower the number of characters in the file. If it's lower than the range, we advise him to increase the number of characters. Okay, so now we have a way to transform our numerical model into a verbal advice. You see, so now we reverse the log transformations we did, because the number of characters, for example, now range from like 0 to 20 or something, but these are not the real values. We see here the distributions, okay, of Shapley values for characters and characters itself. So as we see, the Shapley values for low number of characters are negative, so low number of characters affect the score negatively, and they keep increasing until some point and they return to decrease. This is what we noticed, that characters have a positive effect to a certain end, and too large files tend to have low score. Great. Same for every variable. As you see, they have this U-shaped distribution. So we have positive effect in some range and negative effect everywhere else. Okay, same here, same here. Okay, now we plot this this is a force plot. Okay, we can choose, for example, characters here and also characters here, and we see this characters has negative effect from like 0 to 1,000, for example, and then from 1,000 to 35,000 they have a positive effect, and then they dip down again, and then they have a more positive effect, and then they just keep their negative effect. So we can say that characters has positive effect on the score from like 1,000 to 35,000. Great, we can like see this for all other variables like this. Okay, now it has a positive effect in a very tight range, which is the line length standard deviation. Let's see for the ratio stuff. Okay, this comment ratio here. Okay, same, it has a positive effect until some point and then negative. Let's take a look at some of the binary features. Okay, for the binary features, we don't have them here. Why we only included the numerical features? Because the binary features, they are either a good thing or a bad thing. You can't have them be a good thing in one time and bad in other times. Maybe if they are relative to other features, but in this case, for example, we have having a docstring for your file. This is either a good thing or a bad thing. So it's a good thing. It's a good practice to explain what the file does. Okay, having a long line. This is always a bad thing because it makes readability hard. Okay, so we will only examine the numerical features here. So we have one directional effects. So variables which are only good or bad. They shouldn't have ranges. So long line, bad names should never be good. Too many arguments, unused imports, and there are other features that always should have a positive effect, like docstring, function class docstring ratio. Okay, they should always have a positive effect here. Okay, so now we get range features, which are features that has a positive effect in a certain range. Okay, and we here create a function which get widest positive range. Now, as we see, we determined the ranges of positive effect by our eye, but this is not practical. So let's imagine this scenario. I put my model to production, it performs well, and after some time it degrades in its performance. So I need to do a retraining cycle. So I would have to each time get here and examine the ratios and the effects. I have to examine the effects of each feature and determine by my eye what is the positive range for this feature. So this is time consuming and not very accurate, because what if you start having a lot of features? This is a lot of work, and also some person, for example, when we see for characters here, as we saw before, you have two positive ranges. So which one do you pick? This is this big one or a small one? Obviously it's the bigger one, but what if they are very comparable in size? How do you decide? So moving the decision from a subjective perspective to a more objective perspective is much better, and this is what we do here. So we go to generate recommendations, and we see get widest positive range. This gets the Shapley values and the features I want to get the ranges for, and the sliding window. Okay, what this function does, basically it iterates over each feature from the list I passed as an argument. If it was not task, it just does this for all the features in the model, okay? And it determines the widest positive range. Now, how can it does this where, for example, in a positive range, I can have one value which has a positive, one data point that has a negative effect for this feature, and all other data points in this range has a positive effect. So it doesn't make sense to conclude this range is not positive because of one data point, okay? So how we can deal with this is by have a slight smoothing window, okay? So if we consistently in this window have a positive effect, we conclude that this range has a positive effect, and vice versa, okay? So what are the number of data points to determine on? The default is 5. You can tweak this parameter and play with it to see how it affects the retrieve ranges, okay? So this is the function. If it finds that a certain feature has no positive effect, it replaces its range by the word never, okay? So we apply this function and we try it and we see what it gives us back. So for example, characters has positive effect from 2,200 characters to 36,000. So this is actually pretty comparable to what we found by just looking at the plot, okay? And the same for other features here. Great. Now we combine both range effects with one directional effects to get features positive effects, okay? And now we create dependencies. Why this? Imagine this scenario, okay? I just want to make something clear. I didn't think of all of this when I was doing it, because some people, when they watch a completed project, they think, oh, how did you think of this? No, I didn't. I didn't have this part at all, but in production, when I started using the model and trying it several times, I noticed this problem. Sometimes the model would give me a recommendation to increase function class docstring ratio, but the code I gave to the model already has no functions or classes. So it doesn't make sense if you give me a code with no functions or classes and I tell you need to write more function and class docstring. I don't have any of them, okay? So I thought of adding dependencies. So some features depend on other features. So if it turns out that function class docstring ratio is has a negative effect and you need to add it or increase it, and your code has no function density or class density, I would instead give you a recommendation to add functions and add classes. Does this make sense? Same for code compactness. If you have a very short code, so like a couple of lines, it would have a compactness of 1. But if I told you like decrease the compactness, make the code more spaced, this doesn't make any sense because you have just a couple of lines. It's normal to have them stacked on top of each other. So I make here a dependency of you have effective lines at least 10. The same for the line length standard deviation here, okay? And the same for average class methods. You need to have classes in your code in order to have class methods in the first place, okay? These are not, hard limits. You can change those. They are mostly subjective. They may be, examined. You try the model with a 10 here and try it with like 20, 30 and see where you get the most satisfying performance. So we have now the biggest function of them all, get recommendations. We give it the code in the form of a Pandas series. The function that generates features, the model it will use to predict, the training dataset, which acts as a reference for Shapley values. Don't forget this. This is important. The features positive effect, the dependencies, and the log features in order for it to reverse the log when it's dealing with Shapley values. It returns features, okay, it generated, score of the model, and the recommendations. Let's first let's take a look on the output. So for example, here these are the features. Okay, we saw them before. The score, and let's see, cyclomatic complexity increase, effective lines increase, variable density increase. So now it tells us to increase these 3 variables in order to improve the score we get. Great. Let's now take a deeper look to this function. Okay. First, we get the features and score from the code. We did this before. If the score is -1, means the code is not executable, or the score is 10, means the code is perfect. Just return features, score, and empty recommendations, because if the code is perfect, I can't recommend anything for you, you know. And if your code is not executable, I would tell you, you know, your code is not working, fix it first. Now we do vectorization. We mentioned this before. We get the Shapley values. Okay, we pass the training set as a reference, don't forget, and these are the vectorized features as the input for the Shapley values. Okay, and embedding dimension, in this case it's 0. Okay, it's the default here for this function. If it's not passed, it's 0. Okay, now we calculate the effective lines, because if you remember, it was not apart from our features. Okay, so we calculate it on the fly here. If there are dependencies, we will use them. We reverse the log features here. Okay, now after we get the Shapley values, we will sort them from the most negative to the most positive. Why? If the feature has a positive effect on the score, this is great, I don't need to do anything. If it has a negative effect, means I need to change it. Okay, I should start with the most negative feature, because this feature is the most thing dragging my score down. If I fixed it, I would get the most improvement. Okay, so we start from the most important to the least important. We iterate over the features from the most to least important, as I said. Okay, and I get this feature's positive effect. If its positive effect is always, and its actual value in the code I'm processing is 0, I would recommend increase it. Okay, if its positive effect is never, and it's more than 0, I would recommend to decrease it. Okay, else if it's not always positive or never positive, if it has a range, I would look. If the value of the feature is lower than the range, I would advocate for increasing. If it's higher than the range, I would recommend to decrease it. Okay, so now the part for the dependencies, as I said, check for the dependencies of this feature. If they are there, okay, then recommend increasing the feature. Else, if the dependencies are not satisfied, recommend increasing the dependency itself. Okay, this is repeated here. Okay, so basically this is first check for the dependency. If it's there, then go on and add this recommendation. If it's not there, ignore the recommendation for the feature and add a recommendation for its dependency. Great. Now we would have two similar features. The effective lines is, so I may tell the the user to, you have low effective lines here. Okay, so increase the number of lines in your code, which is the same as saying characters. Okay, and at the same time, maybe the code has low number of characters, so I would then give him the same advice twice. Okay, so to avoid this, if we have both characters and effective lines in recommendations, we just remove characters. Okay, after each iteration, if the number of recommendations are more than 3, so we can just go to the whole list and check all the features to give recommendations on them. But this is, overkill. I just need to give you 3 recommendations. This is more manageable. Okay, so if we at any point have more than 3 recommendations, we will just break and then return the features, the score, and recommendations. Okay, now the last function here is construct recommendations. We then the output, as we saw, is feature and the direction in which to tweak this feature. Okay, we want to make this more verbose. So if I told you, for example, increase your cyclomatic complexity, you may even not know what is cyclomatic complexity and how to increase it. Okay, so this is not very user friendly. So we construct a more friendly messages here. As we see, for example, let's take a look at cyclomatic complexity example. Type of this feature is range. It has a range of positive effect. Increasing message. The code may be overly trivial, okay, because it has a not it doesn't have a lot of if else statements and whiles and loops and so on. Ensure logic is meaningful and not overly fragmented. Okay, decreasing message. The code is complex. Simplify logic, reduce branching, or break into smaller functions. Neutral message. If we decide, if you did something good, we praise you on it. Code complexity looks reasonable. Okay, and this is the same for all the features here. Okay, great. Let's take a look then at the construct recommendation. It takes the score, the recommendations, and recommendation messages here, and returns a message to print for the user. So here we start the message by your estimated score is X. Okay, if the score is -1, not a valid Python code or code contains no logic. Okay, as we mentioned before, if the score is 10, so you got a perfect score, code is perfect, no suggestions. Else, if we have a score between 0 and 10, we start adding suggested improvements and we iterate for every feature in recommendations. We add the recommendation message for this feature, okay, and we add a new line and we return the final message. Great. Now we have a working model, but we don't have any, so we see an example here, estimated score, suggested improvements, and the recommendations there. Okay, we now, since positive effects and dependencies and recommendation messages may change from version to version of the model, we need to keep track of them. And again, as I told you, MLflow is very useful in experiment tracking, so you keep everything under control. So we just connect to the MLflow database, we enter to get the recommendation model, and we get its version, and we just save the recommendation data under this model's version. So now I don't want you to get confused. The model version 3 is in our training, our local training. We trained 3 models, but for MLflow, it currently has only 1 registered model, which is model version 1. So model version 1, not the models we trained, but the model trained via MLflow. Okay, keep that in mind. And then we save these metadata into a model version and the currently deployed version on MLflow, okay, so that we can retrieve it easily. Now we have a working model but the user, wouldn't use Python to interact. We should now create an interface. We won't spend much time on this because this is vibe coded. Okay, the app is mostly vibe coded. We have here front end. You can check it if you want. I don't, personally, I don't know much front end. Let's go into the back end. We also won't spend much time here. The most important thing I want you to focus on is ML, okay, and pipeline. Okay, so what are we doing? Now focus with me. First, we are loading all the functionalities we will need. Now this is everything we worked through until this moment. We connect to MLflow, okay, and we look for the recommendation model at production. This is the model we will use in prediction, okay. We get the run ID of the model and we retrieve the data frame of training. We get the training set. Why we do this? Remember, Shapley values need a reference, so we need also always to keep a reference of data the model was trained on. Now we add a soft limit here because our model trained on data in a specific range of characters, let's say 1,000 to 10,000. If it sees like some user submitted a file with 100,000 number of characters, for example, our model would perform poorly on this example. Why? Because it's trying to predict on something it did not see before. So we just keep it as a soft warning for the user to see, like keep the number of characters below the maximum number the model saw during training. Okay, does this make sense? We now go and get the metadata we would use, and you now see the usefulness of MLflow because I'm not hard coding anything here. So the version is retrieved and the dataset is retrieved and the char limit is retrieved from the dataset. So when I decide to retrain a new model, I don't need to change anything in my app. I don't need to change any path or any name or anything because it's all dynamically retrieved from MLflow. So no matter the number of times I iterate over my model from now, I don't need to touch my app. I just train the new model and automatically each time the app runs, it would fetch the newest model from MLflow. Okay. Now the pipeline for prediction, we get the row, we just get recommendations and we construct the message and we return features, score, message as always, and this time version. Why are we returning these exact 4? Okay, because we don't only want to show the message to the user, we need to save the data about our users in order to make retraining possible. So in any ML environment, what usually happens is this: you train a model on some data, okay, like we did, and then you push this model to production. It performs well for a while. After this, your users start changing their behaviors. This is normal across basically every domain you may imagine. Users start shifting their behavior and the model performance start declining. So what you do is you gather this data from your users and you retrain your model after it reaches some limit. This limit may be dynamic or maybe you hard code it, it doesn't matter, and you repeat the cycle. The model performs well for a certain period and then it declines and then you retrain, etc, etc. Okay, so in order to make this retraining possible, we need to keep the following stuff: features. Why? If I just kept the code our users submitted we can generate the features, later. We can just generate the features. Two reasons here. First, for privacy. So it won't be nice if you tell your user, I'm keeping, your code. We are technically keeping features representing this code, but we cannot reconstruct the code from the features. So if I know the number of characters for this code was 2000, I can't do anything with this information. Maybe I know its complexity, its length, its functions, classes. These are all valuable information, but I cannot reconstruct the code from them. Okay, this is a good thing for your users' privacy. Okay, and the second thing for the returning features is that why spend compute on generating features again? We already generated them once, so we just use what we got instead of redoing the same work. The same here for score, so we don't rerun the model locally on the code, and the same for everything. And we just save the version for versioning, because I want to know which model, because as I said, the cycle contains that reiterating several times. Each time the model declines, so I want to know which model made this prediction. And in larger systems, you may even have multiple models in production at the same time. Each of them, for example, you deploy this model for this region, for these types of users. You may be doing A/B testing. So for all of this, you need to keep track of which model did which prediction. Okay. So this here, we have a simple authentication service. Again, this is not a web dev video, so I'm not be going into that much. Just here, the config, this fetches the character limit from the pipeline, as we said, and if it fails, it just returns a hard-coded limit, just in case. This is a good practice to make sure that you always handle errors, because you don't want your app failing in production. Okay, here when someone submits code, here the pipeline returns what we just discussed. Okay, and we version value here. The version is an MLflow object, which is like a big object containing a lot of metadata. For simplicity, we just would keep the version, which is in this case version 1, if you remember. Okay, and we save the submission in our database. Okay, so this is our database here. Current user ID, submission, features, prediction, model version. Okay, and we return here raw code. We don't save it, we just return it to when the user submit. We want him to see his code alongside the recommendations, so he can go back and forth between them and understand how these recommendations help him. Okay, and he can edit it immediately, not have to go back to his code editor or something. So we don't want the user to go back and forth between the tabs a lot. Okay, this just user experience. I'm not proficient to talk about this, but this is something simple I thought of. Okay, this what everything you need to know about the app. Here the app is we use Docker Compose and Docker. I'm not gonna explain Docker, but simply it's a containerization service to avoid the misalignment between your testing environment, your local environment, and production environment. All of these may have different variables, different versions of packages, and different stuff. So to avoid the headache of code working on your machine locally, and when you push it to production it fails, you just keep everything in like one container the operating system, with the dependencies, with everything. So if it works on your machine, you 100% guarantee it works everywhere else. Okay, this is Docker, for example. It's a great tool. Okay, so this is a bad decision of mine. Okay, why is it bad? Because as you see here, I'm mounting from my machine notebooks, models, MLflow. Okay, I'm mounting them to this specific path. Okay, you may think, what is this path? MMT, SSD, me. Okay, this is the path the MLflow directory lives in my computer. So, and perfectly, this shouldn't be hard coded like this, because this is bad practice. It would work on your machine because I am mounting from a relative path here, but this is this is not good in general. Why I did this? Because I used a local artifact in MLflow for just making stuff more simple, but practically you would have like MLflow connected to an S3 bucket, for example, on AWS, or any any storage any storage service in the cloud, or maybe even a dedicated database. Okay, but for simplicity I kept MLflow local. Okay, so if you ran the app, it would work normally, but I just tell you, this part here is not supposed to look like this in any production environment or something. Okay, now if we want to try the app, we do compose up like this. You will find the terminal command in the GitHub repo if you want to run it through the command. Okay, everything started. Now you open the browser, and you'll find it at localhost 5173, as we see here. Okay, I was already logged in, so we have as we said, users. So we can log in, and if we don't have account, we need account to, so we register. So let's say anything with any password here, create account. Okay, as I said, I'm not a web developer. The security of this thing is terrible. I didn't even review it. As I told you, most of it is vibe coded, so take it with a grain of salt, that we are focusing on the ML perspective more than the web app perspective. Okay, this is what it looks. As we see here, this is the soft limit we are retrieving from the pipeline, as we said. And this character count for our characters here, and this is the Monaco editor. Okay, the same VS Code uses. Here, disclaimer: the backend stores submissions for future model training to improve performance. So it's nice to keep your users aware that you save their data for future training, because otherwise is you're stealing from them. Okay, so let's try typing something not valid just to see. Get recommendations. Okay, as expected, not a valid Python code, or code contains no logic. Now we can back to the editor, or we can just type here again and resubmit. Okay, let's take a look here. Say print hello and resubmit. Now we actually get score back, and we get suggestions for improvement, and we can apply these suggestions as we saw in the beginning of the video, and resubmit and iterate through this cycle until we get a satisfying score for us. Okay, final section now is monitoring and retraining. Until this point, we have covered from idea to execution to product, and now we have a working app. But as I said, ML doesn't stop here. As time goes on, the model performance starts declining, and you start getting more feedback from users. You start getting a more accurate perspective about the real world interacting with your model. Okay, so at some point we need to change or retrain this model. So first we need to stimulate some users, because I don't want to go manually and logging in, using the model and submitting some code, etc. So we used the test split, if you remember, from the dataset we found on Hugging Face. So now we use a training split which has 90,000 examples. Okay, we don't need this much. We format it as we did with the test split. Okay, we extract executable code from it, and we need a sample size of 200. Okay, this is enough for our experiment here. Okay, great. Now we run the app, and after running the app we stimulate users. Okay, let's take a look at this function. So what we need to stimulate users, we need to register a new account with the username and any password. And after this, we need to go ahead and submit this user's code and and this would just save it to the database. And we repeat, we go to the next row in the data frame, get the user's name, submit the code, and go on. Okay, so this function to generate a random password. Here we take the username, submit because it's user. We take the username, the code to submit, the credentials df. What does this do? It's simply if it found out that the user I want to submit code for is already in this data frame, it doesn't create a new row for this user. So this keeps username and password for all the users I submit their code. So this makes me avoid duplicate users. Okay, and here is the API for the app. Okay, so we just does what I just said. We give them a password, we save this password, we register. Okay, and then we log in, and after this we get a token to start our session, and we submit the code, and then we retrieve the new credentials after this new user was added or not added if it was already there, and the response, which is just success in this case. Okay, and here we have the stimulate users function. It just uses the submit code as user multiple times for the data frame we pass for it. Okay, and it just returns the credentials data frame. Here we got the credentials. So out of 200 code pieces, we got only 196 users. So there were actually users who submitted multiple codes, and this is expected for this application. Okay, and now we need to make sure that this data matches what we find in our database for the application. And we connect to the database here, and we retrieve the number of total users and number of total submissions, and we found that number of users is 196 and number of submissions is 200. So this actually confirms that we used the app correctly. Okay, let's move on now to retraining the model. We make sure the app is working. Okay, and now we have the generate report function. Okay, let's see what it does. So simply, first connect to MLflow and gets the specified model, gets the deployed model if not specified. So what we are trying to do is generate a report that explains what is the current performance of our model. Okay, is it good? Is it bad? Do we need to retrain a new model or not, etc. So we first, this function should take the model version here. Okay, if because as I said, we may be using multiple models at the same time or doing A/B testing. So if I did not pass a model version, it just goes to MLflow and gets the deployed model. As you continue, you may you see the importance of MLflow or any experiment tracking software in general. Okay. Then it loads the dataset used for model training, connects to the app and gets submissions that passed through the loaded model. Okay, so only submissions that was predicted using the model version. Okay, calculates pilot score for the submissions which act as ground truth. Now we want to compare the performance of our model compared to pilot, because we trained the model to predict pilot in the first place. So pilot acts as our ground truth in this case. Again, take this with a grain of salt, because pilot is not the ground truth for readability and styling. As I said at the beginning, these are subjective things, but we can assume that they correlate. Okay, calculate the error metric, root mean square error. So we can use mean absolute error or whatever. So I just picked this metric here. Calculate drifts between the submissions and the training dataset. This is very important. If the distribution of the inputs to your model starts shifting, the model would perform poorly. As we said before in the number of characters soft limit example, it's the same for all the features. If the model starts being used for distributions it was not trained on, it doesn't know what to do because he never saw these examples before. So if we start to see a huge shift in distributions, we then should retrain the model. Okay, generate an HTML report containing everything we discussed so far. Okay, let's take a look. Here, so get production model. So let's start from here. Okay, this is the main function. It uses other functions, but we just to save time, you can look at them. So generate report takes the MLflow URI, the database URI, and model version. As we said, these are mandatory except for model version. If it's not provided, it just gets production model version from MLflow. We get the currently deployed model information, which is its old RMSE and the training data frame. Why we get this error? Because we want to compare this error to the error on the data from our users. So for example, if our model had RMSE of 2 and our users data got RMSE of 2, this is an error, but it's the same as the error we expect from the model. Okay, so we don't expect the model to get a better error than this. But if, for example, it got an error of 4 on the user's data, now it got much more error on production than from our training environment. So we then should think of retraining the model. Okay, we get the new data. Okay, and we also retrieve the timestamp for when we retrieve this data, because this acts as a cutoff. For example, I may generate the report and read it sometime in the future. So if I then decided to retrain, I may include new data points from users that used the model after my generation of the report. So this is misleading. I would then account for data that didn't show in the report. So to avoid this, we return a timestamp here to make sure when I decide to trigger retraining, I only get the data until the cut point I generated the report on. I hope this is clear. Okay, we prepare the data frame of the users, okay, like generating pilot score and generating transforming the JSON features into separate columns, etc. We get the new RMSE for the user's data, and we compare it to the threshold. So we here define decline threshold of the performance of 25%. So if the model performs worse by 25% on users' data, we trigger retraining. Okay, and drift threshold we decided to be 20%. If there is a 20% drift, we then trigger retraining. Great. So if the difference is larger than decline threshold times the old error, we say the RMSE message is exceeded, which exceeded the threshold. Okay, and the same for drift. We use evidently. You may use any other software for drift detection and this report generation, but evidently is very good data drift preset. It's the default. Okay, it generates a report and we transform it to a dictionary so we can access it programmatically, and we create a dictionary for drifts. So what columns have a drift more than the threshold? The threshold here is determined by evidently itself. So you have the evidently threshold for each separate column, and our threshold is for the percentage of drifted columns. Okay, so for example, if we have 10 features, if we have 3 of them drifted, then we conclude that we exceeded our drift threshold. Okay, but that the determination for a specific column to be drifted is up to evidently. We can edit that, but we just leave it as it is. Okay, after all of this, we pass our findings to HTML template, which just fills the exceeded, didn't exceed, the numbers in it, and generates a report. We can take a look at this report here. This is the template. Okay, you can take a look at on it. It's mostly vibe coded and reports, and here is the generated report. Let's view it. Okay, so now what it tells us: performance monitoring, old RMSE, it's 2.5, new is 2.39. So actually the model is doing better at the user's data. Difference is that didn't exceed the decline threshold. Okay, share of drifted features, here we see a 66% of drifted features, so like 2/3 of features are drifted, and these are the drifted features and their drift value. Okay, here are the detailed evidently reports, so you can look at certain columns, see what tests for drift was used for each column. Okay, and here if you clicked, you get a detailed plot of the distribution. So you should avoid automatic deployment. Why is this? Okay, so you may have automatic retraining. This is fine, especially if you are dealing with a small model, like in our case we are dealing with random forest, so it's cheap to train. So you basically won't have automatic retraining for a large language model, for example. But deployment, you can do this. Why? Because when you retrain a model, first you need to evaluate it. Okay, you say I would do an automatic evaluation. No, because your new retrained model may optimize for the new data more than it should be, and it would lean toward the new patterns and behaviors in your users' data in a way that may completely how do I say this, piss off your old users. So there may be a trend in the domain right now, and most of users follow this, but your loyal users don't like this trend. So you automatically retrain and deploy the new model, which tries to just minimize the error you present for it, and it works well for the new users. But actually, these users would just leave in a matter of months or something, or in a short period of time, because they are just following the trend. So you try to win the new non-consistent users, and you lost your loyal users. Or in other cases, for like, if a model has something to do with legal work, or law or medicine, these things are uh, dangerous. You can't account for the model to just deploy itself and uh, believe that it would do well in production. So most of the time, it's very good practice to avoid deploying automatically. Always evaluate the model yourself. Do tests. Use the model. Tests could be, uh, misleading. You can get good performance, good numbers, but when you use the model, you find something uh, that is very bad related to a certain group or a certain style of code in our example. So it works well for most of the code, but for this style, for example, it works very bad. And this is not as a good thing. Maybe it's a good thing for the domain you're working on, but you should always investigate the model performance. Okay. So we generated the report here. Then we decide, okay, we want to retrain a new model. This function exactly does this. These are the steps: connect to MLflow and get the specified old model. Okay, loads the dataset, all data frame used for the old model training, connects to the app database and gets submissions, calculate pilot scores for new data frame, which act as ground truth, generates a train test split for new data frame, then combines the training split with all data frame. Why is this? Okay, as I was talking, you don't need to keep following the trends. So you had your model trained on data, and then users used your model, so you have now new data, and you decide to retrain your model. Now, should you retrain your model on the new data only, or on both, train old data and new data? If you trained your model on the new data only, you would be following the trend. This means your model would be very biased to recent data all the time. This is bad. This is not good. So what you should do, you should train it on all the data you gathered until this point. But there's another problem. What if, for example, the old data I was using got outdated? It contained certain patterns, certain behaviors that no one is doing right now. I would be treating them equally important to the new data, and then my model would still be attached to these outdated behaviors and patterns. So we need something in between. We need to account for all data, not throw it each time, and not throw it each time, and at the same time, as time goes, we kind of forget about this old data. This is actually simply achievable by giving weights to samples. So in training any model, you can give each sample, which is a data point or a row, a certain weight. So the model pays more attention to the heavier points. Okay. How can we do this? Do we give a certain weight for each, a fixed weight for all data, and a fixed weight for the new data, or there's something smarter. Actually, there is. You use a decay series. So the older the data point, remember that we know when each data point was submitted. So the older the data point, the less it gets weight. So the newer uh, data points gets heavier weight, more emphasis during training, and older points get less weight and lighter emphasis. Okay, so calculates time decay sample weights for training data, trains a new model using Optuna and MLflow, evaluates both old model and new model on test set, and the test set is only from the new data, so we don't use any test set from the old old data frame. Test set comes purely from the new user's data. And return run ID, so we can retrieve if we want to deploy this model, we can old metrics and new metrics for us to compare. Okay, let's take a look. Okay. Here we are retraining the model. We need MLflow URI, database URI, model version, timestamp. Timestamp is for the, for when I retrieve the data points from the user's database, the cutoff we talked about previously. We get the old model data, we get the new model. Okay, we prepare the data frame, we combine the both training data for the user's data and the old training data. Okay, we combine them, and we do a train test split. We vectorize, we then determine half-life days of 30. What this basically means is after a month the model would have the weight for the training data point. So the more time passes, so after 2 months it would get a quarter the weight, and so on until it's completely forgotten. And we just train the new model using MLflow. If we take a look here, it's the same where we did for the model version 3, if you remember. Okay, the same stuff here, and we log random status size, everything the same, and we also log half-life days because it's a parameter that we can change. And after this we get the old parameter. We can the old model performance on the test set, and then and the old metrics here. Okay, and we return run ID, old metrics, new metrics. Okay, after doing this we find that old metrics here on the new user's data like this, and these are the new metrics. We see that obviously the new model performs better than the old one. So and I said this is not enough for deciding to deploy. You need to consider evaluation more seriously. Okay, like we did residual analysis, looking at certain data points using the new model yourself. But for simplicity here, we just will deploy it. Okay, so these are the functions: save model recommendation data and deploy the model. So save model recommendation data, model version 2. What did this do? If I provide here, it takes model version, features positive effect, so the metadata basically. If I provided metadata for it, it will save it in the same path, which is recommendation data model version. In this case would be version number 2, and then its metadata. If I didn't provide, it will go to the previous model, which is currently deployed on MLflow, and copy its metadata. Okay, so it would use the current metadata. And then after this, I decide to deploy the model. I give it MLflow URI, the run ID, and the model name, which is recommendation model in this case. And it just deploys the model. Let's take a look at the code here. So save model recommendation data, as I said. If it's provided, we save it. If not, we just get the old model data, and like this, we get the old model data, metadata, and save it. Okay, deploy model. Here we connect to MLflow, and we just register the new model at the same alias, which is production. And it says here created version 2 of model recommendation model. Okay, so now we finished this section. Now we are mostly done. There are just a couple of things I need to mention. Tests, I won't go through them, but they are just normal tests for the app, which is API, data processing, feature generation, generate recommendations. It's a good practice to write tests as you're going. Don't get, very stuck in this to try to test something you didn't build yet. So start building after you reach a working state. Write the tests. So in the future, when you are editing something, you make sure you don't break anything. Okay, and here we have, where is it? Yeah, GitHub workflows. This is for GitHub Actions to automatically run the tests for you when you do the commit. This is also another good practice. So instead of you having to remember doing the tests manually, it just be connected to your commit and your interaction with Git overall. So here this on pull request or push, I would trigger to run these tests. Linting test using graph, just for having nice code for conventions, and to run my tests. Okay, so okay, that was it. I hope you enjoyed the video. I know I'm not the greatest speaker. This is my first time recording something this long, recording anything at all. Okay, this is my first time. I hope you enjoyed the video, you learned something. As I said, don't make it a one-sided video. I want your opinion on this. If you have any questions or any modifications, feel free to approach me. I would leave my contact information in the description and or comment on this video. This was it. Thank you.